Thanks. Can people hear me all right? Is the microphone working? Okay, great. So it's standard practice to start talks on verification with exploding rockets. So here you go. But today I actually want to talk about network outages due to misconfigurations. I know that network outages are less sexy than exploding rockets, but they're actually equally expensive and a lot more common. Sorry to be picking on Google, but Google has had at least 3 major outages just in the last couple of weeks. In fact, these outages are so common that I was able to take a screenshot of one. This is not a joke while preparing these slides. Yeah, good luck taking a picture of an exploding rocket while preparing your talk. But luckily there's a solution. It's called, what's the problem? So why do these companies not have their networks under control? You'd expect proficient companies such as Google should be able to control their networks. But the key problem is complexity. So these networks have just become so large and so complex that you can't expect a human to rule out when they make a configuration change that this won't cause any problems. So this keeps going wrong every once in a while. But luckily there's a solution, and it's called network verification. And so this turns out to work very well. So we've heard a lot of success stories out of Microsoft Research and more recently Amazon as well. And arguably network verification works better than general software verification because the problems are a lot more tractable. So let me show you how it works based on a simple toy example. So let's say we want to route packets from a source node on the left to the destination node on the right here, and we've set our network up to take shortest paths through the network. So keep in mind that these network configurations typically are very low level. So we may want to make sure that we didn't introduce a bug in our configuration. And so we can turn the configuration together with a topology, give it to a verification tool, together with some property we're interested in, or some query, like will my packet get delivered? And the verification tool will come back with an answer, either saying no and giving us a counterexample, so we can use the counterexample to debug the configuration, or as in this case, saying yes. And in that case, the tool will have sort of implicitly have constructed a formal proof that the configuration is correct. And so we can be quite certain that it will work. And now we can go ahead and install it on the real network. OK, so it looks like the problem is already solved, right? But there's one more problem. Real networks are fairly unreliable, or, well, not unreliable, but every once in a while they fail. So nodes in the network fail or links fail. And when they do, they drop packets. So one important property you want to reason about is fault tolerance. And it turns out that traditional tools are really not equipped to reason about fault tolerance. So let's say we assume that links in our network fail with probability 1 independently. So the best traditional network verification tool can do now to answer our questions whether packets get delivered is to say maybe. And while that's technically correct, it's also not very helpful. So this is where our work comes in. So we designed a probabilistic network verification tool called McNetKAT. And in this case, it can tell us that packets get delivered with roughly 98% probability. So that's a lot better. So now that we have a tool that can actually reason about things like fault tolerance, let's make this toy example slightly more interesting. So in practice, people employ what are called resilient routing schemes. So these routing schemes try to locate errors and then route around them, so that even if links fail, packets can still get delivered. And so let's say that in this case, whenever the next link on our path fails, we'll just select a random neighbor from the reachable neighbors uniformly at random and try to reroute around the failure that way. And let's also assume that at most 2 links in the network will fail. Under those assumptions, McNetKAT will tell us that packets will actually get delivered with probability 1. And so what McNetKAT has figured out here is that this routing scheme is what's called too resilient. So as long as at most 2 links fail, turns out the network is always connected, and this routing scheme will eventually find a path to the destination. So to understand how McNetKAT figured this out, let's look at a concrete failure scenario a little more in detail. And it's actually kind of surprising. So if you look at this example, we can actually end up in an infinite loop around the network. So say we start taking our first hop along the shortest path, But now the next link on the shortest path is down, and so we'll take a random detour. We might end up going to the top node where the shortest path is the link on the shortest path is again down, and so we might randomly decide to send the packet back to the source node, and so on. So we can actually end up sending the packet in this infinite loop around our network, and yet McNetKAT said that the probability of delivery is 1. So why is that? Well, the key thing to note here is that every time we leak, so taking a loop around, taking one iteration in this loop has probability strictly less than 1. And so as we keep taking more and more loops, the probability decreases, and in the limit it will be 0, right? And so eventually, with probability 1, we'll exit the loop and the packet will get delivered. Okay, so, but this raises the question, how can we automate this kind of reasoning, right? So we'll have to reason about infinite paths and probability that vanish in the limit. The key observation here is that a packet being routed or forwarded by a probabilistic network is a lot like a random walk, right? So the packet somehow takes this random walk through the network. And so when random walks are very well studied in the literature under the term Markov chains or probabilistic transition systems. And so we can use this formalism to describe this. And there's a lot of nice tools for analyzing these Markov chains. And in particular, we can compute closed form for these limiting distributions that we saw in the previous example. And so we can actually figure out the exact probabilities by solving some system of linear equations. So this is great. This solves the problem on paper. But there's some challenges in implementing this. So if we look at the state space of this Markov chain, one component of the state space is the location. And that's of manageable size, maybe 1,000 nodes, maybe 10,000 nodes in a really large network. We can deal with that. But another component of the state space is the state of the packet itself, the header space. Turns out that networks route packets depending on the values of their headers, and sometimes they rewrite the headers. And so we need to keep track of those header values as well. And there's a lot of them. In fact, more than particles in the universe. And so there's no hope that we could explicitly build this Markov chain. Okay, so how do we deal with that? So the observation here is that this Markov chain is far from arbitrary. It's very, very structured, and we can exploit this structure, right? So one thing is that the transition structure is very sparse. So a network doesn't rewrite packets in arbitrary ways, but in sort of very limited and controlled ways. And it will typically only look at a few header fields to decide where to send the packet. So somehow many of these states will have a very similar transition structure. So there's a lot of symmetries here that we can exploit. And without going into details, although I'll show you a few more details on the next slide, the take-home message here is that we can exploit all this structure and build a tractable, a scalable verification tool using some clever data structures. I'll show you how it works in a second. Okay, so let's look at how we actually implemented this. So in McNetKAT, we start from the network model. And in McNetKAT, this is actually specified using a domain-specific programming language called Probabilistic NetKAT. So this is a probabilistic language for describing network behavior. You can use it to encode the forwarding schemes, resilient routing schemes, as we saw in the examples, but also the topology of the network, and things like failure models. In general, programs in this language can describe fairly complicated probabilistic processes, and you need full-blown measure theory and domain theory to give a mathematical model of this. But in our work, we identify sort of a tractable fragment of this language, such that all programs from this fragment are, mathematically speaking, just very well-behaved finite-state Markov chains. So at this point, on paper, we're actually done, because these Markov chains are easy to analyze. There's all kinds of tools in the literature. But as I mentioned previously, the state space of these Markov chains is way too large to actually compute them explicitly. But what we can do instead is compile the network program into a symbolic intermediate representation. And here we borrow some ideas from earlier work where we showed how to compile NetKAT efficiently, build a related data structure. So you can think of this as just a very compact representation of this ginormous Markov chain that exploits the symmetries and all the structure to represent things in a very compact way. So we can use this data structure to efficiently implement things like sequential composition and probabilistic choice and some other primitives in this programming language, but we can't use it to compute limiting distributions. So in order to do that, we can convert the intermediate representation to a sparse matrix representation, and then we can invoke highly optimized linear algebra solvers that are optimized for such sparse matrices, and then compute limits by solving some sparse linear systems. And then convert back and forth between the two representations as necessary to compile the entire program into one explicit representation. Okay, so at the end of the day, we're not actually interested in these data structures, but we want to answer some verification questions, right? And that's actually, once you have compiled everything, is straightforward. So we wrote some custom code to analyze the symbolic intermediate representation, but you can also use standard tools, linear algebra tools, to analyze the sparse matrix if you prefer. And so this turns out to be very cheap compared to compiling the program. And so we can answer many questions after we've done the compilation step, which is sort of where we spend all the time. Okay, so with that, let me show you how this works out in practice. We wanted to make sure that this is not just a toy tool, but that we can apply it to real networks. Real networks are really large, and we wanted to make sure that we can run this on large networks, and we can. Let me point out that there is a significant cost to modeling failures. So you can see that the green line with failures doesn't perform quite as well as the yellow line, but we're still able to scale to really large networks. So this works quite well. One really cool thing about McNetKAT is that we can parallelize things very well. So we can parallelize across multiple cores on a single machine, or even across multiple machines in a cluster. And you can see here that we often get near optimal speedup. So for example, we used 40 cores across 3 machines, and we got a 30x speedup. And on 60 cores, this was, I think, on 4 machines, we got a 40x speedup. So often, we get really good speedups through parallelization. So that's quite useful. We also compared to state-of-the-art tools and showed that we're orders of magnitude faster and more scalable. And we did an extensive case study where we looked not at a toy example, but a resilient routing scheme that was proposed in the literature, and ran this on a real data-centered topology. And we looked at properties such as probability of delivery, resilience to failures, and the latency. Because sometimes when you route around failures, right, you'll end up using a longer path. So one question that's important to answer is how long can these paths get? But for details, I'll ask you to refer to the paper there, please. So to summarize, McNetKAT is the first scalable verification tool for probabilistic networks, and that means that in contrast to deterministic verification tools, it can reason about things like fault tolerance. McNetKAT is based on the theory of Markov Chains, which provides a solid mathematical foundation and allows us to compute limiting distributions in closed form, so analytically. Now, implementing this requires a bunch of tricks because these Markov chains are very large. We used sparsity of these Markov chains, and we used some symbolic data structures to exploit symmetries. We showed that this can be parallelized really nicely, and we used some optimized linear algebra solvers to compute these fixed points. So with that, that's all I have, and I'm looking forward to your questions.
So you were mainly talking about these resilient routings, and I saw ECMP on your slides where you have this probabilistic forwarding thing. I was wondering, in real-world networks, you often have these more high-level routing schemes like BGP, which is used often, or MPLS, whatever. And at the beginning, especially when you showed these issues with outages in real-world networks, a lot of them are caused by BGP problems, for example. I was wondering, to what extent does your work apply to this scenario where you look at more high-level routing scenarios?
Yeah, I mean, we think of these models as mostly modeling the data plane, not the control plane. But in practice, there's these proposals for data centers where you have sort of resilience at all levels. So you have some resilience built into the data plane, And then you have some resilience at higher levels where the control plane recognizes failures and then will install new rules. But often this is sort of at a different time scale, so it takes much longer. So yeah, we probably, well, we can sort of accurately model things like BGP or higher level control plane mechanisms, but it's sort of more focusing on the data plane here.
More questions? Actually, I have a question.
Mm-hmm.
So you mentioned that you have to make some independence assumptions. And since I know very little about networks, I don't know how dependent or independent failures tend to be.
Mm-hmm.
And so can you maybe elaborate a little on that and also on how flexible you are about what kind of dependencies there might be?
Yeah. So in our example, we assumed that links fail independently. This was basically just to make the example simpler. There's no reason why we couldn't model dependent failures in general. It might be a bit harder because you will need more data to have some sort of reliable statistics on what you think the dependencies are. But yeah, our tool in principle can reason about dependencies as well. It's not a problem.
I had a quick question. So, I mean, it's very interesting. So, like, you'd like to try to look at like this kind of reduction to apply to like prism-style transition system. Also,
yes.
I mean,
Mm-hmm. Yeah, so we actually we implemented two backends. One is sort of our custom backend that I was showing on the slides. We also implemented translation to Prism. And in some instances, well, we basically slightly outperformed Prism. So we believe that sort of having this custom backend can be quite valuable, given that well, Prism has been optimized, for decades, and we built this one-off implementation, and we're a bit faster.
I meant like implement like this kind of optimization in Prism in probabilistic model checking.
Oh, so they already do use similar optimization.
Right.
So they use similar data structures as we do, based on binary decision diagrams.
Right.
Sparsity, I'm not sure, but probably I'm not really sure if they exploit sparsity.
Yeah, I haven't seen with the sparsity. That's
yeah. That's
okay.
a good question. Yeah.
All right. So let's thank the speaker once more.